Last one, problem 4. It says check your integrals. I think the only one that's really bad is part B. I will go over all of them just so that we feel comfortable. Okay, so part A, we have a sine of x squared is the really annoying part, but except it's not that annoying because if you just say u equals x squared, then taking differentials of both sides, du equals 2x dx. So that x dx, and let's actually just write that, x dx can be replaced with 1/2 du. So what we're going to do is we're going to replace sine x squared by sine u, and then we're going to replace x dx with 1/2 du. That 1/2 can come out in front. I'm taking the integral of sine u du. You don't have to write all these steps. I just am because I'm recording a video and I don't know how fast you're following. So integral of sine is negative cosine. I'm going to write my plus c, and then u was x squared. So I have negative 1/2 cosine x squared plus c. That's part A. Not so bad. Okay, part B, this looks terrible. This is the integral of secant squared x tan squared x dx. Okay, that's secants and tans scare me, so I'm going to write, oh, actually, no, we should keep it because most of you have tan, the derivative of tan memorized. Okay, let's do it that way. Okay, so if you figure this out, this is the easy way to do it. Otherwise, you've got to do a lot of double angle stuff. Okay, I didn't figure that out until just now. So du is going to be secant squared x dx if u equals tan x. This is the easiest way to do this problem. So then the secant squared dx is du. This is u squared. That's super nice. Du, which is going to be 1/3 u cubed plus c, which is going to be 1/3 tan cubed x plus c. Okay, let me just go over at least a summary of what I was going to do before I realized that we could do that. This was going to be, I didn't know what to do with the secant squared, tan squared. Sometimes you can still solve the problem if you don't know how to do, if you don't figure out the best way. But what that was going to become was sine squared x cosine to the 4th. And I don't know what to do with that, but I do know sine squared is 1 minus cosine squared of x. So now I can split this up, which is not better. But this might have worked out. I didn't try it all the way to the end. I just thought in my head that about what I was gonna maybe do with this. So even odd powers of sine and cosine are good because you can always turn those into a u substitution. Even powers are annoying. And usually what happens is you end up using a double angle formula. So cosine 2x is 2 cosine squared x minus 1. So like I could replace my cosine squared x with cosine 2x plus 1 over 2. In this case, I'm not even sure that works because now I have a cosine in the denominator, and that's no good. Okay, so maybe that way doesn't work. That's another possible strategy that might work for some integrals. I'm not sure if it works for this one. I did want to show you some ways, other ways of maybe attacking this if you didn't see the super clever thing. But obviously the best way is to find the super clever thing. So I'm glad I thought of that. If I didn't, I'd keep messing around with this for a while and see if anything came of that. I'm not 100% sure it will. I might have turned the 1 into sine squared x plus cosine squared x too, and then at least gotten rid of fractions and seen if that was any better. That probably would have been better. That's the nice thing, is 1 is sine squared x cosine squared x. So if you have like cosines at the bottom, you can always like keep replacing 1 with sine squared x cosine squared x, and you won't have cosines at the bottom anymore. Like they'll just, you can increase the powers of cosine. So things in the bottom might not eventually be an issue. Anyways, if you can avoid all that mess, you should. Part C, the integral of natural log x over x dx. This one's a little bit easier to see the trick to, because if I just let u be a natural log of x, then du is 1 over x dx. So now this is the integral of u du, actually. That's all we got. So this is 1/2 u squared plus c, and I just need to sub log back in. You know, it's weird that sine x squared is sine squared x, but I've never seen anyone write log x squared as log squared x. That's not common notation. So I don't know what that is. Don't write that because people won't be sure what you mean. Part D, the integral of sine x dx. Okay, so this is starting to be annoying. I need to do integration by parts. The idea of integration by parts is that if I can't integrate, maybe I can take the derivative of one of the things and be able to integrate. So what I'm going to do, I like to do this without writing a formula, but I've also done this a lot of years. I want to take the derivative of that one. So the first thing I need to do is take the integral of the other thing. Okay, so that's negative cosine x, and this x is still here. Then I'm going to subtract, and I have an integral. I have the negative cosine x because I took the integral of that thing. Now I can take the derivative of this thing. If this is too ugly, if you can't follow that, just write out whatever you normally write, the UDVs or the F and Gs. I'll show you one of them. So like I can write f of x equals x because I want to take the derivative of that. G prime of x is sine x dx. So g of x is negative cosine x, and then f prime of x is dx. Okay, so then maybe, what am I doing? I guess if I'm writing it this way, I have to write the f prime of x dx here and g prime of x dx. Okay, so then I'm putting in f of x, g of x, minus, and then I had these ones. So I want the product of the other two over here. That's what I got. Okay, so then this is negative x cosine x plus the integral of cosine x dx. Integral of cosine x is positive sine x. I don't have to write the plus c until I've gotten rid of all my integrals, so that's nice. All right, that is part D. And then one more. It's going to be exactly 3 times as ugly as this. Because I'm going to need to do 3 integrations by parts. So the integral of x cubed log x dx. If you know how to do that table where you like take the diagonals, and in one column you keep taking derivatives, and the other column you keep taking integrals, that's fine. I can never remember how to do that, so I'm going to do what I just did over here. If you want to write f's and g's or du's and dv's, that's fine. I'm just going to do the thing I just did, which is I'm going to take the integral. I want to take derivative of this. So first I'll take, wow, okay, I don't want to do that. I want to take the integral of log x. No, I want to take the derivative of log x. It's not 3 times as ugly as the other one. That's good. Okay. I'm going to take the integral of x cubed. So I'm going to get x to the 4th over 4 times log x minus the integral. I'm leaving this x to the 4th over 4. Okay, this is very nice. Then I take the derivative of log x. If you do this FG thing, this is what you will get. Okay, but then I don't have to do, okay, if it were x cubed sine x, I would have to do integration by parts 3 times. Since it's x cubed log x, I don't. So this is just x cubed over 4 dx. So this I can integrate directly, which is great. So now I have x to the 4th over 4 log x minus, this is going to be x to the 4th over 16 now, because I'm dividing by another 4 plus c. Okay, so that's not too bad. Yeah, so I stand by what I said. Part C is probably the trickiest one, and I guess that one's not even so bad if you saw the trick right away. Oh, sorry, part B. was the hardest one, is what I meant. But hopefully that's a good review of integration techniques, use substitution, integration by parts. I did a little bit of trig substitution in my previous video. You won't have to do more trig substitution than that, so you can probably get away with just having the things memorized that I don't have memorized. And let me know if you have any questions about derivatives or integrals. Happy to make more videos to clarify anything here or do more problems on one specific technique.